Hello and welcome. In this video you will see the Reynolds equation, finally. After these long derivations, the last step is now to insert the result that we obtained from the Navier-Stokes equation, namely the velocity field, into the continuity equation for an incompressible fluid, and that continuity equation has been written with respect to cylindrical coordinates. However, we do not insert directly the velocity field into this continuity equation. Before we do this, we multiply the continuity equation by r and we average by integration in radial direction. Why do we do this? Well, because you can't hope or can't expect that we will be able to solve the continuity equation sharply, so locally, after the introduction of so many simplifying assumptions as we did here. So therefore, we just want to satisfy the continuity equation in average. That appears to be enough for our tasks. So we multiplied by r and we integrated, and now if you look at that equation, so maybe you would say, but it looks at the beginning a little bit different. So what happened to these two terms? Where if you have a close look, then you observe that you have applied here a product rule for the product of r, v sub r, and the derivative with respect to r. If you take the derivative with respect to the first term in the product, so to the first factor r, then you obtain the second term, namely just v sub r. Keep in mind we multiplied the whole equation by r. And if you then take the derivative with respect to the second part, so to v sub r, then you obtain exactly this term multiplied by r, which is here. Yeah? Okay, so we summarize these two terms in one term, and that's the averaged continuity equation. You can imagine that the computation of these integrals is quite involved, and therefore we split this computation in three parts. We compute each term separately. So there's just some space here on that, slide. So I would like to start here with the first integral, this one. So we integrate from r minus h to r, that expression. For v sub r, we insert the result that we obtained here without expression of v sub r, capital V sub r, so without these expressions that we obtained at the end of the last video, just without the integration constant and with the general solution of the simplified Navier-Stokes equation. Then it amounts to this expression where we have to take the derivative with respect to r. The first lowercase r is that one here, and the term in parentheses, capital R minus r, comes from the solution of the Navier-Stokes equation in radial direction. So if you remember well, there was a parenthesis, capital R minus r, that is used to satisfy the boundary conditions. So you have to take the derivative with respect to r, but you integrate with respect to r. Well, then things are simple. From the fundamental theorem of calculus, you obtain v sub r divided by h, and then it is just the term inside the derivative, lowercase r, times capital R minus lowercase r in the bounds of capital R, r minus h, that we have to take into account, or that we have to take to evaluate here. And then we have minus v sub r h, h r minus h. Well, we can simplify that result. Again, we have a difference of capital R minus h, but r is much larger than this tiny little lubrication gap. So we replace the parentheses by capital R, and of course 2 times h here will vanish. So we have minus v sub r times capital R as the result here. Okay, first integral was quite simple. For the next integral, let's move to the next slide. okay, which is this one here. And observe that the calculation of the integral now becomes much more involved because, well, the integration is now still with respect to r, but the derivation inside of the integrand is with respect to phi. And the boundary here, so the limits of the integration, they depend on phi via h. So the upper limit clearly depends on phi. How can we solve this problem? Well, maybe we do first some computations and then we think about solving that problem. Let's plug in the expression for v sub phi, and let's at the same time substitute, namely the difference of capital R minus lowercase r by y. If we do this, if we substitute, then we would get here for the lower bound and h. For the upper bound we would get for the lower bound we would get we would get h. For the upper bound, here it is, for the upper bound we would get 0, but if we replace the differential dr by dy, we would get a negative sign, so d sub y is equal to minus d sub r. So we use that negative sign that we get from replacing the differential to change the order of the limits and to not integrate from h to 0, but just from 0 to h. And then finally we can plug in everywhere in these parentheses where capital R minus lowercase r appears, we can just replace it by an y. Yeah, this is here the case in the first term, and this is the case in the second term where we have y times y minus h. Okay, small substitution, but the problem remains. Now it's the upper bound, the upper limit h here in the integral that depends on phi, and we would like to interchange that derivation and the integration, and this is not allowed. Or I would say it's not allowed to just interchange and switch this because of the dependence of the limit on phi, but it is allowed if you apply a special rule of calculus which is called the Leibniz rule. Therefore I recall this rule. It can be seen as an extension, as a generalization of the classical fundamental theorem of calculus to the case that you have a differentiation here with respect to x. You integrate over some other variable, y, as is the case here, but your integration limits depend on that x. And now you would like to interchange this. And if this dependence would not be there, you would simply obtain this integral. As there is the dependence on the limits on x, what you get is you get a negative term for the upper limit, which is fx minus b, and then the derivative of the upper limit with respect to x plus the lower limit fx and a dA by dx. Or one could say that this term is equal to the interchange term where the differentiation is now, or derivative is now inside the integral, plus upper limit minus lower limit if you put these two terms on the left hand side and read the equation from the right to the left. So this is the idea of Leibniz rule. Yeah? Perhaps you have seen it in engineering mathematics, at least I hope so. How do we apply this rule here? Well, here we have a simplification that the lower limit a does not depend on x. So we can drop the last term. So we just have to take this interchange into account, and then we have minus fxb dB by dx, which amounts dB by dx to dH by d phi. Okay, so the whole expression is, well, this is our tiny right-hand side before, that we want to express. So it's the second term in this integral. The first expression here is obtained by putting the d by df phi on the left of the integral here, and then integrate, well, the remaining term with respect to y, which is just a simple polynomial that you have to integrate with respect to y. So the first one is even a linear one, leading to half v sub phi h. The second one is a little bit more involved. If you do the computation for y times y minus h in the limits of h and 0, you obtain the h cubed divided by 6. And the rest are then just the coefficients that are copied. And until now, we obtained the first term in Leibniz rule. We need to evaluate also the second term. And the second term means that, first of all, we have a negative sign. It's there. We have to take into account dB by dx, which is dh by d phi, which is there. And finally, we have to evaluate the term inside the derivative. So everything that is in that parenthesis that starts here, by plugging in our y equal to h. If you set y equal to h, then no sorrows with the second term, it's equal to 0. For the first term, it remains just v sub phi h divided by h, which is v sub phi. So therefore we have minus v sub phi dh by d phi. Okay, this was the most difficult integration here. We move to the third term, which is then again simpler. We have the integral capital R minus h, capital R dvz by dz, d sub r. And here it's nice that the integration limit does not depend on z, on our axial coordinate. So therefore we just plug in the expression for v sub z, which is capital R minus y, d by dz, 1 divided by 2 pi, d pi dz, y minus h. If we do the same substitution as before, if we substitute r minus uppercase r minus lowercase r by y. And again here we then exchanged the integration limits and profited from a change of the sign here. Well, that integration can now be easily done. So the derivative can be put in front of the integral, and then you have a certain polynomial here to integrate. And we simplify this integration even further because we observe there is again an expression where we have a capital R minus y. So this can be represented approximated by capital R. So then we have the same expression as before, y times y minus h to integrate, and this yields h cubed divided by 6. So with this simplification, we replace that parenthesis by r, that r moved in front of the h cubed divided by 6. The rest is copied. The sign is negative. We obtain minus d by dz, 1 divided by 2 mu dp by dz. Okay, now let's assemble the whole story on the next slide. In total, what we found is minus v sub r capital R plus d by d phi half v sub phi h minus 1 divided by 2 mu r dp by d phi h cubed divided by 6 minus v sub phi dh by d phi. All the story comes from the second term, minus d by dz, 1 divided by 2 mu dp by dz, r h cubed divided by 6 is equal to 0. This must be the Reynolds equation, but believe me, it's not in a nice format, not at all. There are still our rigid body velocities, v sub r and v sub phi included here, and also the ordering of the terms, well, could be improved, I would say, right? So let's try to put all the derivatives of the pressure, because the Reynolds equation governs the pressure field, put them on the left-hand side. all the terms that are the first, the second one, and that one here, that are independent on the pressure, we will put it on the right-hand side. And in order to write it a little bit more nicely, I will multiply the whole equation by 12. You will ask, why by 12? Because, for example, 2 times 6 here and 2 times 6 here, and these are the important terms, the terms that govern really the pressure field, derivatives of the pressure field. They include 2 times 6, so a 12 in the denominator. So therefore, multiply by 12 and divide by R. Then what we get is the following. Well, let's look that we do not overlook any term here. So the first one on the left-hand side is the derivative of the pressure field pi with respect to phi. We have dp by d phi, h cubed, the 6 and the 2 gone away by the multiplication with 12. The r is still there, so h cubed divided by r and by mu. We have another derivative with respect to phi that sits there, and we said we multiply by 1 divided by r, therefore the leading factor of 1 divided by r. You see the advantage of multiplying by 1 divided by r in the second term here. I would say it's a cosmetic result. Okay. Yeah. So this r goes away here. The 12 goes away by multiplication with 12 divided by r. We have dp by dz. We have an h cubed divided by mu, which is here, and we have another d by dz. Okay. So the left-hand side is done. Now we look at the right-hand side, or we put these terms with a positive sign here. So we keep the sign of these terms that are here on the left-hand side, so the negative sign. We multiply by 12 and divide by r, so we get minus 12 v sub r. Next one, this one, from the second term, we multiply by 12. No, it's not that one. I'm sorry, it's that one here. Yeah. We multiply by this one here. We multiply by 12, we divide by r, minus 12 v sub phi dh by d phi. And now the last one is this one. We multiply by 12 to yield a 6. We divide by r, which is here, and we get d by d phi v phi times h. The left-hand side is already perfect for the Reynolds equation. It shows to you already that the pressure field is governed by a linear partial differential equation. That partial differential equation is linear in the pressure. There is, of course, some kind of nonlinearity included in the coefficients here, in the h cubed, and that's terrible, but the expression in the pressure, there is no squared pressure, no third power or whatsoever, no sine of the pressure or cosine of the pressure. The pressure by itself is linearly included. And the derivatives are perfectly separated. We have one term with derivatives with respect to phi, the other term with respect to z. Everything is nice there. What's yet not that nice is the right-hand side. Because it includes term in v sub phi and in v sub r, and in the first step for v sub r, we can include the result that v sub r is minus dh by dt, that was the translatoric part of the radial velocity, minus the v sub phi divided by r dh by d phi, which was the rotational part. And well, if we do this, if we plug in this result, then we get here, first of all, 12 times dh by dt. And now let's look at the other terms. Observe that we have to apply here the product rule, dv phi d phi. And we have another 6 d v phi dh by d phi. Here we have minus 12 v phi r dh by d phi. So we drop the second term, and we just copy the last term, which is 6r d by d phi v phi h. And then we can replace V sub phi by omega times R, and this would then be the Reynolds equation. Now, is it easy to solve that Reynolds equation? It's a linear partial differential equation, and the derivatives are well separated in separate terms. No, it isn't, because of that h cubed here. Keep in mind that if you have such a situation where the derivatives are really separated, you can always apply Bernoulli's separation theorem that leads to ordinary differential equations. But these ordinary differential equations have to be solved and have to be adapted to the boundary conditions. And that's the difficult point here with the h cubed. And therefore these solutions exist, but they fill not tons of paper, but pages, many, many pages. And practically they are not used, but the Reynolds equation is simplified for two cases, which I will show you on the next slides, at least one, but how to derive these two cases. And that solution is then nice and quickly to compute, and that's in general used. Okay, so how is that done? Well, before simplification of the Reynolds equation, I would like to add the boundary conditions, and then we write the Reynolds equation in a dimensionless form, and then we even simplify and solve the dimensionless Reynolds equation. So without the boundary conditions, the Reynolds equation wouldn't be complete. It wouldn't be even possible to solve the Reynolds equation, or it would be only possible to get a general solution but not adapted to boundary conditions. What are appropriate boundary conditions? Well, the pressure field depends on the circumferential coordinate phi and on the axial coordinate z. So we need boundary conditions in axial direction and in circumferential direction. In axial directions, things are quite clear. You assume that you have ambient pressure, so the pressure difference, which is P, is 0 at the two boundaries, which is, well, if B is the width of the bearing and you start with your coordinate system in the center of the bearing, you have minus B divided by 2 plus B divided by 2, and you are at the boundary and you have ambient pressure, so the pressure difference vanishes. Easy. Now we move to the circumferential direction and a quasi-static consideration of the shaft, so the shaft sits there. And we measure the angle theta here. So we start at the point, so theta equal to 0 points to the situation, to the angle, circumferential angle phi, where the gap is the smallest between the shaft and the bearing housing. It's exactly the point where you change from a convergent lubrication gap to a divergent lubrication gap. In the convergent gap, you will have the pressure here. According to the Sommerfeld condition, you set at the opposite point, so at the opposite end of the bearing, you set the pressure also to 0, leading to a pressure here in the convergent part and to a pressure valley in the divergent part. Well, I hesitate here a little bit because that pressure valley with negative values for the pressure difference can't exist in practice. What will happen? You will have a rupture of that fluid film. The lubricating film, there will be cavitation due to underpressure, and blob, the oil film will just explode, and it will not be possible to maintain this negative pressure range here. The idea of Gümbel, therefore, was to use the Sommerfeld boundary conditions, but to remove the negative part of the pressure, and that amounts to setting already the pressure to 0 at the point theta equal to 0. So at that point where the convergent part of the lubrication gap moves or changes to the divergent part. And to keep theta equal to 0 at the opposite end. And to set the pressure to 0, or do not compute it, just take that hill into account for all the other situations, so for these situations here. That's already good. There is no, or that takes cavitation to a certain extent into account, but it's not perfect. Why? Well, because there's another problem, and the problem sits exactly at theta equal to 0. If you look at that figure, then what you can see is that at theta equal to 0, the pressure distribution in circumferential direction has a kink. Therefore, it's not differentiable at that point. Well, you would perhaps say, that's a mathematical problem. I don't care. I'm an engineer. Well, you should care, because this affects physics. Where do you need pressure derivatives? For example, in the Navier-Stokes equation, pressure gradient, that has consequences for the velocity. And you need the continuity of the velocity field inside the continuity equation. So this is a hard violation of physical reality. And therefore, there is another often used boundary condition, which is the so-called Reynolds boundary condition, where you do the following. You want to have a smooth transition from that pressure hill to 0. So you apply that 0 boundary condition, not exactly at theta equal to 0, but at a position where the derivative of the pressure with respect to the circumferential coordinate vanishes. So where you have a horizontal tangent here approximately of the pressure function of the pressure distribution with respect to the circumferential coordinate. This boundary condition has also a disadvantage, but it's not a physical one, it's a, I would say, mathematical one. While you can nicely evaluate the Sommerfeld and also the Gümbel boundary conditions, you can't for the Reynolds boundary condition, because you do not know beforehand where to apply that boundary conditions. That requires a numerical procedure, an iterative procedure, in order to determine the position θ1, where you have the horizontal tangent, and there you then apply in the second step the boundary condition. And due to the boundary condition, that point may change again, so you need an iterative procedure. Therefore, in the following, we will use the Gümbel boundary condition, which appears to be a good compromise between physical reality, which is not true for the Sommerfeld boundary condition, and mathematical complexity, as opposed to the Reynolds boundary condition. And now, let's simplify the Reynolds equation and let's apply, let's solve the Reynolds equation then. Well, in order to simplify the Reynolds equation, I would like to introduce dimensionless quantities in order that the values or the magnitudes of the terms can be better measured. How do we arrive at dimensionless quantities? Well, for the axial coordinate, we take a length scale. The appropriate length scale would be the width of the bearing. So we set z bar equal to 2z divided by b, so that z bar runs from -1 to +1. For the lubrication gap, a good quantity would be to divide it by the clearance C. So we introduce a dimensionless lubrication gap, which is just the lubrication gap divided by clearance. A dimensionless time can be introduced, though, by just multiplying the physical time by the rotational velocity. And well, the last term is d divided by 2r, which is of course not a dimensionless term, but which is just introduced here for classical purposes. It's often used. The diameter is much more frequently used than the radius for the bearing housing. And then there is the pressure. And in order to understand how we introduce a dimensionless pressure I would say it's very hard from just looking at the term that, oh, this is the perfect dimensionless pressure. We rather have a look at the Reynolds equation, introduce these dimensionless quantities, and if all the other terms here on the right-hand side are dimensionless, then we must get a factor that leads to a dimensionless pressure, because one side of the equation is dimensionless, the other side has to be dimensionless as well. So before we do this, we multiply the Reynolds equation by omega and divide it by c. And what we get is the following. Well, maybe we start at the very end of the right-hand side of that equation. We do have here 6 divided by r. Taking the omega divided by c into account, we get omega times v sub phi divided by r. V sub phi is again omega times r. So we get do we divide here by we multiply by 1 divided by omega times c. This is wrong. This is nonsense. So we divide by we multiply by 1 divided by omega and c. So then what we have here in the last term is from v sub phi we get r times omega. Divided by r we still get omega. Divided by that omega we get 1. We have the lowercase h, which is h times c, h divided by c. So lowercase h is replaced by capital H times c. And then as we divide also by c, we get uppercase h. So we get this expression. Next term. Again, we have capital H, we have lowercase h before. It is replaced by capital H times c. As we divide by c, we get the quantity h from which we take the derivative. We would take the derivative with respect to time t. D by dt would be d tau by dt, d by d tau, which is then omega times d by d tau, d by d tau, yeah, d by dt would be d tau by dt, which is omega times d by d tau. So we get omega times d by d tau here. We divide by omega, so this is completely wrong. It's multiplication by 1 divided omega c to get 12 divided by dh by d tau. Okay, let's have a look now on the terms on the left-hand side. Maybe we start with the first one. Now, well, we have dp by d phi, capital A, lowercase h cubed, which is then replaced by capital H c in the third power. So in total, what we have here is we divide by c, so we get c in the second power. We divide by omega, so in the denominator we get omega times c in the second power. We have in the denominator an r squared, we have a mu in the denominator, and that's all. So we get a c squared in the numerator, a p in the numerator, and in the denominator we have an r squared mu omega from the division by omega. So, and if you look at now capital P, that is exactly the quantity that we need here for capital P, as all the other factors are already dimensionless and the right-hand side is dimensionless. This must be a dimensionless quantity. you can insert all the physical units of that quantity and do the computation. Well, for the ratio C divided by R, it's clear. But for the pressure, the pascals, and for the viscosity and for omega, and then you see that this is indeed a dimensionless quantity. Let's move to the last term, to that one here. Well, this is now the term dZh in the third power divided by mu dp by dz. Well, first of all, we replace h cubed by capital H c cubed. We divide by c, so this leads to a c squared, and to the pressure. In the denominator, we will find mu, we will find omega because we divided by omega, and then we need, in order to introduce the dimensionless pressure, we will need in the denominator an r squared, leading to an r squared also in the numerator, because we haven't an r squared ready there. So this leads to r squared here. Finally, we have to transform the derivative with respect to z in derivatives with respect to z bar. This leads to a factor of 2 divided by b, as we have to do this twice, 2 divided by b squared. The 2 we use to multiply with the r to yield then d. Therefore, we have d divided by p squared, d by dz bar, h cubed d pi divided by dz bar. And this is the dimensionless Reynolds equation. Now, what can be said about the order of magnitude of these terms? Well, perhaps you would say that, well, if we look at D and B, you would say, well, the right-hand side is independent of D and B. That's quite clear. It just includes the capital H, which is depends on the basically on the eccentricity E, but not on D and on B. You would say the second term depends on the ratio D divided by B squared, and the first term is independent on D and on B. And this is not true. Well, the result for the right-hand side is true, but not your conclusion for the left-hand side. Have a closer look at the left-hand side. You see the capital P here. You see the definition of the capital P. And what's inside that definition? An R squared. So the first expression is of the order of magnitude then of 1 divided by R squared, which is of course the same order of magnitude of 1 divided by D squared. Difference would just be a factor of 4, which is negligible. Okay, so the first term is of order 1 divided by D squared. The second term, due to the fact that in pi you have to divide by R squared, is of order of magnitude of 1 divided by B squared. As the right-hand side is independent on D and B, you could do the following. Either your D is much larger than B, then what you would obtain is the second term is much larger than the first term because it's of order 1 divided by D squared. So you have a large diameter, but a rather small in width bearing. Then the second term is dominant. In opposite, you have a very, very wide bearing with a small diameter. Then the first term is much more larger than the second term. This is called, the first example was called a small bearing or bearing of small width, and the second one is a large or wide bearing. And what we will use here is that small bearing assumption. And then what you see, it's so-called short bearing theory. What you can see that for this short bearing, you just have one of these derivatives. And then the solution is easy to obtain because it's just the second order derivative integrating twice the right-hand side plus, of course, the the factors included here, and you have the solution for the dimensionless pressure. And from the dimensionless pressure, of course, you would be able to compute the dimensional pressure here. Yeah? Okay, so therefore these things are easy to solve if you can switch off one of these two terms, and that's possible for the short or the wide bearing. And that's called the short and the wide bearing theory, and we will consider here only short bearing theory. Let me show to you this on the next slide. So the first term is of order 1 divided by d squared, second term order 1 divided by b squared, right hand side independent of d and b, and now move to the short bearing theory. So we just keep the second term of the left hand side of the Reynolds equation, and we keep the right hand side of the Reynolds equation, and then we integrate twice. That's nicely done. We put b divided by d squared on the right hand side, and we write it as a classical term. This term is independent of the z. It's like a motion with constant acceleration. So you get 6 divided by 2, 3, h cubed sits there, b divided by 2 by d and squared, the inverse of this one, and then 2 dh d tau plus dh d phi, z bar squared plus c1z plus c2. The two integration constants, they have to be determined from the boundary conditions now in axial directions. We do not see the boundary conditions in circumferential direction here. You could say, oh, that's nice, because we do not know which boundary condition to apply, whether Sommerfeld or Gümbel or Reynolds, but believe me, it will appear later on, namely at the point where we integrate the pressure field over the circumference, because we want to compute the bearing forces. You cannot escape that problem, but for the moment, for the determination of these two integration constants, you can be happy that we for a moment escape that problem, and for the whole video we escape that problem. Yeah, that's good. Okay, so from the vanishing of the pressure at plus minus 1 for the dimensionless quantity z bar, so the boundary condition in axial direction, we could deduce this condition, but we can also write this as being z squared minus 1 times this variable or factor. This allows us to reproduce this factor, and on the other hand, the z squared minus 1 allows us to exactly reproduce these boundary conditions. Here it is written with a negative sign and 1 minus z bar squared. Okay, so this would be the result for the dimensionless pressure. The result, as you can see, depends on the lubrication gap on capital H, which is just lowercase h, divided by c. Let's introduce this result, and this will be the last slide of this video, and let's interpret what we see for the pressure. So where does that pressure come from? Okay, so H, capital H, is just lubrication gap minus divided by C, which amounts to, here there would be capital C divided by C, that is 1, and here we would have minus E cosine theta, cosine phi minus gamma, and if we divide by C and replace the quantity E divided by C, the dimensionless quantity, now by an epsilon, and call this the eccentricity ratio, then this would be the result for capital H. In order to introduce this result into the dimensionless pressure, we have to take derivatives with respect to phi and with respect to dimensionless time. With respect to phi, things are simple. We just have to take the derivative of the cosine, which is a minus sign, so epsilon sine phi minus gamma. We have to take the derivative with respect to tau. The derivative with respect to tau, now dimensionless time, on which epsilon and gamma depend, is now marked by a prime. So we get first the derivative of E with respect to tau, which is minus E prime cosine phi minus gamma. And then we have to take the derivative of the cosine function, and inside the argument of the cosine function sits this gamma, which produces another derivative with respect to tau, so minus e gamma prime, and from the cosine we get then sine phi minus gamma, so sine minus sine phi minus gamma. No, we don't. Okay, thus putting everything together, we get 3 times b divided by d squared. You can see in the denominator the h cubed, 1 minus e epsilon cosine phi minus gamma cubed, here, capital H cubed. You will find here 2 times epsilon, 2 times dh by d tau with a negative sign. So 2 times epsilon cosine phi minus gamma is the first contribution from minus 2 times dh by d tau. The second contribution is a little bit difficult to see with the sign. It's a positive sign here, minus 2 times that one, epsilon 2 gamma prime, sine phi minus gamma. And you have a minus dh by d phi, so minus epsilon sine phi minus gamma. And we have 1 minus that bar squared. I think we switched the sign here of that expression. How can we interpret this result? So, first of all, if we look at what drives that pressure, then we have to look at the numerator of this expression here. The denominator is just h cubed, but the numerator stems from these derivatives. What can be said about these derivatives? What is the h by d phi? Changing h with respect to phi is the displacement. So it's the lubrication gap that changes with circumferential direction, and that change with circumferential direction is the displacement due to a static load. Because everything else includes time derivatives, and this is the time-independent part. The time-independent part would be even there if these velocities are zero. That will be termed in the next video a equilibrium position. So even if this is zero, you will find an influence on the pressure, and this can then be only due to static things, because it's time independent. So dh by d phi must be a displacement due to static load and must be the influence of the static load on the pressure. It's minus e sine phi minus gamma. So the first part of the second term. Then we have 2 time-dependent effects. The one is in a radial direction and the other one is in circumferential direction. In a radial direction, what will happen if you move in a radial direction with a positive velocity? So outside, you will squeeze the oil film, the lubrication film. So this is a squeeze film effect due to the radial velocity. That first part, and it is seen here. It is doubled, that part. And then you have an influence on the circumferential direction, which is then due to some kind of time dependence in the circumferential motion, and that's called a whirl motion. So it's important, for example, in balance vibration. So this would be the third influence here. So in summary, you see that the pressure, albeit here the dimensionless pressure, is due to 3 effects. It's due to a static load, it's due to a squeeze film effect due to radial velocity, and it's due to a whirl motion, which is of importance, for example, for imbalance vibrations. Well, now what we have to do is we have to obtain the restoring forces by integration of that pressure field in axial direction. That's easy, just a simple polynomial. And in circumferential direction, it seems to be a little bit more difficult due to the fact that well, you have nonlinear functions of phi, and you have a denominator that is not very nice. So Then we have the restoring forces, and then we will linearize the restoring forces around that equilibrium position, an equilibrium position that is defined by the vanishing of E prime and gamma prime. And this is shown, first of all, the derivation of the restoring force is shown in the next video, and then the linearization is shown in the last video in this section for this chapter. Thank you very much for watching this video, and stay tuned. Goodbye.